I want to make a couple of comments about this particular table. This is table B14. You will recall from the lecture last time that table B14 is for compressed liquid. So compressed liquid water. So if we go back to this schematic, B14 is for this region to the left of the two-phase dome, and it's for compressed liquid. I told you that it works pretty much the same way as the superheated table. That is, you start out, it's divided up into subtables, and each subtable corresponds to a different pressure. So when you compare it to this one, to this graph, each of the subtables in the compressed liquid table would correspond to each one of these red lines, which are constant pressure lines on the compressed liquid side. But one thing about this table is that it is very limited. So as opposed to if you look at the superheated vapor table, it's very complete. It goes over several pages, and it has many subtables for a fairly fine delta P, so your different pressure lines. Whereas this one has big gaps between the pressure lines. So for example, if you look at this one, there are the 4 subtables here. The first one is for 500 kilopascals, and then the next one is for 2,000. So it's a big jump in pressure. And then it jumps up to 5,000 kilopascals, and then 10,000. So if you are somewhere in between, suppose that your pressure is 1,000 or 700 or 1,200, somewhere in between, then you would have to do some interpolations, which gets tedious. So there is a way to, and sometimes you just don't have the data. For example, if you just have a small amount of compressibility, for example, maybe it's only 200 kilopascals to give you a lower pressure. You may not even have a table because there is not enough of a compression there. So the way to handle that situation is by paying attention to this note, which is a note regarding the compressed liquid table. So what I just said is this, that the table has limited data. It's not a very complete table. But then this observation becomes very important. Recall that when we were talking about liquids and so on, or from your past experience, you know that the liquid specific volume is a lot more sensitive to temperature than it is to pressure. So if you take a liquid, which we would call, if you take water, for example, at room temperature, that's compressed liquid. And we know that if we increase the pressure, we don't really change the density or the specific volume a whole lot. It takes a really large increase in pressure to make an impact on the specific volume. However, it is a little bit more sensitive, or a lot more sensitive, to temperature. So if you change the temperature of the liquid water, even though the change is going to be small, that sensitivity to temperature is larger than the sensitivity to pressure. So with those two observations in mind, then we can go back and do our plot like we have been doing. So here is a plot of temperature versus specific volume showing what's going on in the compressed liquid side. So I put an open circle there. That's our data point. That's the state of the system that we're working with. And therefore, it is at some temperature T1, and it is at some pressure P1. And those two pieces of information would be sufficient for us to determine the state from the state postulate, because the temperature and the pressure are independent intensive properties, because I am on the left side of the dome and I'm a compressed liquid area. So let's say that's my data, but as I go to the table, I wouldn't find that particular pressure and temperature listed. So there are two things that I can do, taking into account the fact, as I wrote here, that the specific volume depends a lot more on temperature than pressure. I could make two approximations. I could, given that I have temperature and pressure, I could, for example, ignore the pressure value and read the volume as if that system were a saturated liquid. So that would mean that instead of reading the value at my open circle there, or which would give, of course, the value that I put at the bottom here. Whoops. I hit the wrong button. Let's see. It should come back. Sorry about that. I went into some menu mode. But I don't know how to get out of. Let's see. Maybe what I'll do is I'll turn it off and then back on. And hopefully that will bring it back. There we go. So so here is the, blow it up a little bit. So here's my real point, here's my real volume V sub 1, but if I ignore the pressure and just take the value of the saturated liquid at the same temperature, then I would be reading on the table a value that is corresponding to this blue, this filled circle. So that would be the volume that I denoted here at the bottom as V sub F in blue. And if I do the opposite, that is, if I just follow the pressure, so I take the same pressure but disregard the temperature, then I would be reading, and I'm reading the saturated value, then I would be reading a value that corresponds to the red circle, and that would be the one that I am calling down here, V sub F. So obviously, if I have to make a decision about which one to use, then the real one being V1, then of course the V sub F that I read at the same temperature is a better approximation than the V sub F that I read at the same pressure. And the difference is a lot more actually than what you see here, because this is just a cartoon. If you actually use the real table, the real data, you would see that the blue V sub F is a lot closer to the V sub 1 than the red V sub F is to the real V sub 1. So the bottom line is that what you have to do, and the two cases are denoted here at the bottom. So in blue, use the same temperature, read the value of V sub F by ignoring the pressure value, or use the same pressure, read the value of V sub F by ignoring the temperature. But that's the wrong choice. That's why I put a red X. So you don't want to do that. What you always want to do is what is written there. So you just, given the pressure and the temperature for that compressed liquid, you will read the value of the specific volume from the saturated data, from the saturated table data, V sub F, at the same temperature, ignoring the pressure, because the effect of the pressure is very small. You will find yourself many times having to make this approximation because you just don't have data on the compressed liquid, but you have a lot of data on the saturated liquid values. So the V sub Fs, there is plentiful data, but not so much on the equivalent V sub 1. All right? So this will become obvious starting next chapter when we start solving problems. Any questions? Okay, what I thought I would do next is do another example problem. And I picked one from the homework that is due next week. I wrote the statement here. So we're starting now to see problems that are a little bit more interesting than the ones you did, that you turned in today, which were just warm-up problems involving basic concepts. So piston cylinder arrangement, loaded with a linear spring and open to the atmosphere outside. It contains water at 5 megapascals and 400 Celsius. So we have two properties for the water in the cylinder. And we're also given the volume, the total volume that water occupies. Then we're given another piece of information. It says if the piston is at the bottom, so that means all the way down, when there is no water in the cylinder, the spring exerts a force such that it would take 200 kilopascals of pressure to lift it. So if I don't have any pressure at the bottom, obviously the piston is just at the bottom, I would have to have a pressure of 200 kilopascals to start pushing that piston up. It would take that minimum to move it up. So that's just an extra piece of information that is going to help us solve the problem. And then we're told that the original system that has the water in it at 5 megapascals, 400 Celsius, is now going to be cooled down until it reaches a new pressure of 1,200 kilopascals. And then we're asked to find the mass of the water in the cylinder and the final state. And for the final state, we're asked to provide a final temperature and a final specific volume. Then we're asked to plot this on a PV diagram. This is a typical problem in this part of the course. So here is a schematic of the problem with I have some water there, piston spring open to P0, some atmospheric pressure on top of the piston. The data that I was given, pressure, P sub 1, 5 megapascals, temperature sub 1, 400 Celsius, and the volume, V sub 1, 0.1 cubic meters. And the extra piece of information that I gave you, that it takes 200 kilopascals to lift the piston if it's sitting at the bottom. So when this piston is all the way at the bottom here, it won't move up unless I have at least 200 kilopascals of pressure underneath. So we start from there. And then we're told that we're going to cool this down. Obviously, it is at 400 Celsius, so if I just have a lower temperature outside, it will cool down. So I want it to cool down until the pressure inside drops to 1,200 kilopascals. And I'm asked to find the mass of the water and the final temperature and final specific volume. Okay, so what should I do first with the data that I have? Or what can I do first with the data that I have? How about right there, next to the sleeping friend? What can we do? I never bother the people who are sleeping, so I just bother the ones next to them.
Could you repeat one more time?
Yeah, what can we do with the data that we have? What could we try to find out with the data that we have? Let me ask you a question. Do we have the state 1 determined? Do we know exactly what the state 1 is? Because it's asking us to do a plot. So suppose that I say, well, yeah, I want to do this plot. I'm going to get started on this plot. So I'll say, which plot is it that they want us to do? I forget. A PV, all right? So I say, okay, that's a little. So I'm going to do a PV diagram. So here's my dome. First thing that we should be concerned with is, where is 1? Where is state 1? And what would be your guess given the data that we have? 5 megapascals, 400 Celsius. The temperature is 400 Celsius. That's warmer than hot, significantly hotter than room temperature. And the pressure, is that a high pressure or low pressure? How many atmospheres is that? 50 atmospheres. So it's a pretty high pressure, but it's also a high temperature. So where do you think we are? And if we don't know where we are, how do we find out where we are? Okay, so I go to the table. What do I look for in the table? So I have 5 megapascals. Let me see, I should have a table that will be useful here. So that is 5,000 kilopascals. So if I look at this table, I could start with a saturated table, or I could just go into a superheated table. So if I go to a superheated table, and I would go to this one, for example, and look at the subtable for my pressure, 5 megapascals, which is 5,000 kilopascals, I already have a temperature there in parentheses, 264. What is that temperature? Saturation temperature at that pressure. So that's already an answer to my question. Where am I then in the regions? Am I compressed liquid? Do I have a mixture of liquid and vapor? Or do I have superheated vapor? I have superheated vapor because immediately I see my temperature is 400, so it's higher than that. In fact, if I just look down the table, I see that I can find an entry for 400. So I have 400 Celsius, 5,000 kilopascals. That means I am here, because I can find that data point here. So I can just read that number, 0.05781 cubic meters per kilogram, and that I know that's my initial specific volume. So I can come back here to the plot and put a dot for 1, and I could put all the numbers that I need. So I could put my my pressure here, which I know is 5,000, if this is in kilopascals. Right? And there'll be a temperature line there that I could draw. And also the volume that I just read would be, of course, the volume down here at the bottom. That's the V sub 1 that we just picked from the table. So I know now my initial state. So what happens if I now start cooling this down? And therefore, there's going to be a process. Where is that process path? Here. Which direction is this path going to go from 1 if I start cooling the system down? Is it going to go straight down? What will happen here if I start cooling this water, which is actually now we know it's water vapor, right? But if I start cooling it down, what's going to happen to the piston? The piston is going to come down, right? So that means that I cannot be going straight down, because that would mean constant volume. So where do I go? Somehow down, but then also to the left. But do I know exactly the shape of that path? Is it some curve, or would coincidentally happen to be a straight line? Anybody thinks it could be a straight line? What do you think? You don't think it would be a straight line? You? You think it would be a straight line, and why? Because you have no idea. Okay? Anybody thinks that it's a straight line and has an idea why?
Is it a straight line because of equation PV nRT?
No, we haven't talked about our friend PV nRT. So we don't know that yet.
Would be a straight line until it,
Why only until it condenses? Okay. Anybody else? Anybody knows the answer? Yes?
Because of the springs pushing down on it, which keeps it at a constant pressure.
If it were a constant pressure, then it would be horizontal to the left, right? Because that would be constant pressure, right? So all I'm doing is checking to see if you remember what we did last week. But we did this last week. That is our problem. And I won't repeat the story because we already did that. But at the end, the bottom line is that we found out that in a problem like this, you should know how, so you should go over this. Eventually, you find this equation, that the pressure is some constant plus some other constant times V. This is capital volume, but for me, it doesn't matter because specific volume will be volume over mass, and the mass of this system is constant. So it is a straight line. So we already knew, but we forgot that it was a straight line. So that means that the process is going to have to come somehow to the left as a straight line. What I don't know at this point is what the slope of that line is. I need to know the slope of that line. Because I do know another piece of information. I know that the process will end when the pressure reaches 1200 kilopascals. So I could also put here 1200 kilopascals. And I know that when that red line intersects this constant pressure line, that's the end of the story. All right? So what I need to know is what the slope of this line is. And can I determine what the slope of that line will be in this problem with the information that is given? Yes, let me go back to the, you want this or the actual statement? Well, this is a summary of the statement. Oh, that's the one that you want to see? Well, so here is that formula. C1 plus C2V. The C1 is P naught plus mg over A. Right? A would be the area. We don't know what that is. G, of course, we do know. M, we're actually asked. One of the questions is to determine the mass. K is the constant of the spring, and then A again. So we don't have the spring constant either. Could we find M? Could we find the mass of this system now? How? We were given the volume, and we just found out what the specific volume is. So we can get the mass. The mass is not a problem. We can get the mass. Let's put it here, mass, okay. But not the area or the spring constant. We don't have that, so we couldn't use that formula. But, of course, the information that you need is in this statement, that it takes 200 kilopascals to start moving that piston up if it happens to be sitting at the bottom. That information is what you need to find out the slope of this line. How so? No. When the piston is sitting at the bottom, it'll take 200 kilopascals to push it up. What do you think? Forget it. It's not going to be through the spring constant at this point. Just think about what I'm saying. When the piston is sitting at the bottom, it takes 200 kilopascals to start moving it up. What happens if the piston is sitting at the bottom? The volume is 0. Good. And if it takes 200 kilopascals to start moving it, then doesn't that mean that at 0 volume, I would need 200 kilopascals to start things going, and therefore that straight line has to go through that point. All right? That's the key. So once I know that, then, I was going a little bit off here. I can fix that a little and know that really I would have to go that way. But of course, for me, the story ends there. I don't need to go all the way down. Yes?
So we're starting the piston at the bottom and then we slowly add water?
We're not. We didn't see that part of the story. When we came to see the experiment, water vapor was inside the piston, and it was already full. All right? And we then started cooling the system down, so that piston is going to move down. And then we're told that we're going to end this experiment when the pressure is 1,200 kilopascals. That's it. We haven't seen the empty cylinder, but we're told that in the setup that we're working with, if the piston is sitting at the bottom, I need at least 200 kilopascals of pressure to push that piston up. So that piece of information is the extra piece of information that has nothing to do with our actual process, but allows us to determine the slope of the process line. All right? I'm not going to be in a situation like that because that would mean that I don't have anything in the cylinder. Right? So I'm not going to be in that situation unless I start extracting the water, but I'm not doing that. Right? So now that I know the slope, because I have 2 data points, I already have this point and I have that point, then I draw my line and then I know where to end, because remember I said we end at 1200. So my process, of course, this is not part of my process. I can forget about that. That was only used to determine the slope. My process is from 1 to 2 in this direction, in a straight line. My line doesn't look very straight, but it is a straight line. So, of course, that means that now state 2 is completely determined, because now I can find V2. And what is V2? Well, I can just get it from the straight line. Once I know the equation for my straight line, because now I can actually, with the data that I have, I could actually, if I wanted to, write the pressure equation this way, C1 plus C2V. I already know what C1 is. What's C1? 200. Okay? And you can determine C2, which you need as the slope from the data that you have. So now that I have this equation, I can, now that I have C1 and C2, I can put 1200 for the pressure and get the volume. Actually, I would write it with a specific volume. So it wouldn't be this C1, and the equation would actually be, that one is written in terms of total volume, but I would write P equals C1 plus C2 little v, because that's the one, that's my plot. My plot is P versus little v, not P versus capital V. But anyway, I can get C1 and C2, and then put 1200 for P, and I can back out my V2. All right? So now that I have V2, I'm all done, because I can now find out where I am exactly. Right? So I will let you finish it by plugging in the final numbers and so on, and then determine where the actual final state is. That's part of your homework. Any questions or any other questions about this problem? Okay. Let's see. Okay, so what we have learned so far, and this has to do with this topic. I'm going to talk about state equations. Somebody mentioned something about PV equals nRT. And I said we haven't talked about that yet, but we will. But this is what we know so far. We know that if we are given 2 properties, property 1 and property 2, and I just leave it like that, very generic, any two properties, 1 and 2, as long as they are intensive and independent, the state postulate tells us that that allows us to find any other property that we want. In this case, I'm just calling it property 3. So given property 1 and property 2, which are intensive and independent, I know that I can find property 3 and obviously also property 4, property 5, any other property. And I know it's going to be a function of those two properties only. I don't need anything else. I just need those two properties. That's sort of a mathematical way of writing the state postulate. Okay, so from what we have seen so far, this can be expressed as tabulated data. So the tables that we have been working with are nothing but a tabulated way of expressing this equation. Because I go with two properties and I get any other property. Or it could also be actually written as an equation. Rather than this generic function of property 1 and property 2, I could have an equation. For example, here's an equation that is a simple, relatively simple example of a state equation. It says that, for example, it's written in terms of pressure. Pressure P is equal to what you see on the right-hand side. It has two terms, RT over V minus B minus A, and then there is this quadratic expression down here. So you see a bunch of parameters there. In fact, there is A, B, C, and D. And those parameters would have to be adjusted, maybe to the particular substance that you're working with. You also see R, which is the ideal gas constant. So that's a typical, simple, relatively simple equation of state. And again, it has the same effect of the tables. If you have the parameters A, B, C, and D for your substance, you can plug them in there, and you can plug in two properties. For example, you can plug in your temperature and specific volume and back out your pressure. It's an example of this general expression. Now, of course, you can kind of recognize something there, which is what? What happens if A, B, C, and D are all 0? A, B, C, and D are all 0. What do you get?
When you have no system, it doesn't matter.
I'm sorry?
Then you don't really have a system.
No, but just think of the mathematics for now. You have this equation of state, and suppose you're told, well, A, B, C, and D are 0. What do you end up with?
Ideal gas law.
Ideal gas law. Right? So, well, that means that the ideal gas law is an equation of state, a very simple one, because as you can see, it's a much simplified version of this. So, in fact, somebody, when I was talking about the previous problem, actually gave it to us in this form. Right? I actually said PV equals nRT. Right? Ideal gas behavior. So what do we call an ideal gas? Well, an ideal gas is one that obeys that equation of state. PV equals nRT. Now, there is a requirement. So, this is one of those equations that students love, and they want to use it for every problem. In fact, we just went through an example, right? We were doing a problem with the steam. Somebody immediately wanted to use PV equals nRT. There is a requirement that for you to use PV equals nRT, the molecules of your substance have to be very far apart from each other. So the density has to be very low so that for that to be happening. Molecules, because essentially it's like the molecules are independent of each other. Of course, they collide with other molecules and so on, but they're sufficiently far apart. So it requires that the gas have a very low density. Now, and of course, this R with a bar on top is the universal R, the universal gas constant. That's just a constant, it's just a number. You know that already. Put it right there. In SI units, 8.3 kilojoules per kilomole Kelvin. Those are the units in SI. That's the value in SI. That's universal, any gas. Okay, but if we think about what I wrote earlier, I said I said property 3 is a function of property 1 and property 2. does this equation have that form? How many properties do I see there? PV equals nRT. How many properties do you see there? Two, which two? P and V. That means you're blind to the right-hand side. How many properties do we see there? Three. Four. I like four. What about N? Number of moles. That's a property. So there are four properties there. What happens, are there any, some that are intensive and some that are extensive, though? Which ones are intensive? Of those four, which ones are intensive? Temperature is intensive. Which one?
Volume?
Is volume intensive? No. Number of moles intensive? No. Because the number of moles is like mass. So P, of course. Pressure is intensive. So pressure and temperature are intensive. But volume and number of moles are not. So how do I... there's another piece of information, of course. The so-called molecular weight is the mass over the moles. Right? So I could bring that in. So I could rewrite the number of moles as mass over molecular weight, and I can write it like this. Right? And then, if I do that, then this is another form of writing this equation. So P equals VRT. All right? So this R, of course, is not the universal gas constant, because this R is going to be different for every other gas, because it's the universal gas constant divided by the molecular weight. But for a certain system, it is a constant. For a certain substance, it is a constant. So now this equation has the shape that we want, because what we really have there is how many properties for a given substance? Three. Now we have only three, P, V, and T, and they are lowercase v, and they are all intensive. So this actually has the form that we were trying to portray with this general equation. Because I could solve for the pressure, for example, and write P equals rho RT. I write density instead of specific volume. So it has exactly this shape. If this is pressure, and then property 1 and property 2 are, for example, density and temperature, then that has that shape. So that's the ideal gas law. You can write it around any other way you want. You can solve for rho, solve for P, solve for T. It doesn't matter. What you have to remember is the conditions, or the statement that was written at the top here, that the density has to be low enough that intermolecular distance is large. So if you write it this way, density equals P over RT, then you can see what is needed for the density to be low. Because if I solve for density is P over RT. So what do I need to happen for the density to be low? I wrote it here on the right-hand side. Well, I could make the temperature sufficiently high. The higher the temperature, the lower the density. That's good. Or make the pressure sufficiently low. The lower the pressure, the lower the density. And that's the way you have to think before you decide to use the ideal gas law. You have to determine if the temperature is sufficiently high or if the pressure is sufficiently low. However, what do I compare it with? What do I compare my pressure with to find out if my pressure is sufficiently low? Or what do I compare my temperature with to find out if my temperature is sufficiently high? Does anybody know the answer? No. What other possibilities can you think of? Well, it turns out that you compare with the critical values. So for each substance, and I was pretty sure I had a table here. Let me double check. Yeah, of the critical value. So you compare your temperature to the critical temperature for that substance, or you compare the pressure to the critical pressure for that substance. Does anybody remember what the critical pressure of water was? We saw it last time.
0.6.
No, you're thinking of triple. We're at the top of the dome, right? The critical properties are at the very top. So grab any picture of a dome right here. We're talking about the properties at the top. What was it for water, the pressure? 220 atmospheres. So that's just for water. There is a table that you can check in your text. And I just printed it here, where you have a number of substances, a large number of substances. And you have the chemical formula first, the molecular mass or molecular weight. And then these are critical constants. So this is the critical temperature and the critical pressure. It also gives you the critical specific volume, but the ones that we need for testing, if we can use the ideal gas law, are the critical temperature and the critical pressure. So they're there. So if you go down and look for water, right there, there is the 22 megapascals. Sorry, too big. Water, 22 megapascals, which is 220 atmospheres. So then you have the temperature, 647 Kelvin. These are in Kelvin, and these are in megapascals. So if you're dealing with any other substance, then this is the table that you would have to check, because you're going to compare your temperature and your pressure with the temperature and pressure of the critical point for that substance. And then that determines whether you can use the ideal gas law. Okay, let's do another simple problem. And here's the statement. I think this is in your homework too. So I wouldn't probably do the whole thing, but 282. Okay, so it says a 1 cubic meter rigid tank with air at 1 megapascal, 400 Kelvin, is connected to an air line, as shown in there is a figure somewhere that looks like this. And this is way too big. All right. So here's the tank, 1 cubic meter. It has air at 1 megapascal and 400 Kelvin. And it's connected to this line that carries air. There is a valve. Okay. So this line that carries air at, it says here, where is that? Well, it says that this line, this valve will be open so that there will be flow. And then the flow will go from the line to the tank until the temperature inside is 450 Kelvin. Right? And it also says the pressure. The pressure will reach 5 megapascals. You can pretty much assume that that is the pressure in the line, even though it doesn't say it explicitly. Because it says well, assuming that, yeah, if the valve is open and left open, then the air will flow in until the pressures equalize. And so if the pressure in the line is 5 megapascals, then once the tank pressure reaches 5 megapascals, there will be no more flow. But we know that the final pressure is 5 megapascals, and the temperature will be 450 at the end. So we're asked to find the mass of air in the tank before the valve was opened and then after, at the end of the process. And then there is a part B. Now the valve is closed. We let the tank cool down to room temperature. What is the new pressure in the tank? Right? So that's the problem. So here's the rest of the statement. All right? So, so how can we do this? We have air at those conditions. So if we go back to this table, of course, we're not going to find air, right? Why is that? Because it's a mixture. But we already said the other day that we can treat air as a pure substance, even though it's a mixture, as long as the mixture is the same everywhere. So what is the next thing that I can do, since obviously it's a mixture? What gas should I look? Nitrogen, because it's the largest fraction. So I can go to nitrogen, N2, and look at the critical temperature and critical pressure. And then I can make a comparison right there. So for example, let's look at the pressure first. The critical pressure is about 3.4 megapascals. 3.4 megapascals. And our pressure is initially lower, but not a lot lower. 3.4 to 1, a little less than a third. But at the end of the process, it's actually 5 megapascals. So from 3, it's actually higher. So if we go back to our test to see if we can assume ideal gas, we have a problem with the pressure. It's not meeting that condition. But then we check the temperature. And the critical temperature, what did I say, was 126 Kelvin. And what is my temperature? Is initially 400 Kelvin, then goes up to 450, and then it will cool down to 300. But I'm always above the critical temperature, like at least three times, around 3 times, if not more. So that seemed to be okay. So, you know, I can probably do ideal gas, use the ideal gas law. And so that's the reasoning when you're doing a problem like this. So I took it and I put them right there. Critical pressure is 3.4 megapascals, but critical temperature is 126 Kelvin. So that's the one that I go, okay, I'm going to take that as a good measure for my temperature being sufficiently higher. So I'll say, okay, I'll do it as an ideal gas problem. Here's my ideal gas law. And therefore, I can immediately answer the first question, which is to find the mass initially in this tank, because I have the pressure, I have the temperature, and I have the volume. So, and of course, this is the gas constant for air, because now I'm doing the problem for air. I'm sorry, yeah, the gas constant for air, which is the universal gas constant over the molecular weight of air. So I have that. So I have everything, I can get the mass. You can get the initial mass. So what happens after? As the valve is open, mass flows in. Can I get the second mass? The answer is yes, because they gave me the final pressure, and they gave me the final temperature. And the volume, of course, doesn't change. The volume is the same. So with the final pressure and final temperature, I can get the mass at the end. All right, so that's part A. What is the mass of air in the tank before and after the process? We're done with that part of the question. Part B is, if I now let the tank cool down to 300, what is the pressure in the tank? That's also straightforward, right? Because I know the final temperature, final volume stays the same. I can find the final temperature. So that's easy. That's just a very straightforward application of the first law. I'm sorry, of ideal gas law. Yes?
For the homework, when we're plugging in our values, if we did not plug in the units,
Remember I told you last time, don't forget the units, it'll cost you.
but at the end, the final number does have the units.
Yeah, for the homework it's probably okay. As long as your answer has units, the intermediate steps, the TAs probably won't worry too much about that. Just on the exams, just maybe be a little bit more careful.
I have a
What? Oh, well, yeah. It is PV equals nRT, but which R? Where's, here. PV equals nRT. But which R is that? Which R is that? Huh? Question back to you. Huh? Which R is that with the bar on top? Somebody help him. Universal gas constant. And which R is this that appears in this equation? The specific gas, right? The specific for that gas, right? So it's the universal constant divided by the molecular weight. This is all stuff that you gotta know already. I'm just going over it because I know some of you don't remember it. But does anybody else have a question? Okay, so what happens if when we do the test, to see if the temperature is sufficiently high, higher than the critical temperature, or that the pressure is low enough compared to the critical pressure? What happens if that test fails? So I do my test for my properties, and I find out that it's not safe to use the ideal gas law. What options do I have? If I happen to have a table for that substance, that will always be the most accurate choice because the tables are accurate. That will be suppose you don't have the tables for that substance. For example, for air or nitrogen, since we were looking at nitrogen, there is well, I think there might be a table on nitrogen, but pick a substance that there is no table for. Then you have two options. Use the ideal gas law anyway, because you got nothing else, and maybe try to get an estimate of what the error might be, or do something better. So you could go back and try to see if you use a better equation, like the one that we had a while back. Maybe you can get a hold of the parameters A, B, C, and D, right? Or there is another one, which is a modified equation of, a modification to the ideal gas law. And that modification uses something that is called the compressibility factor. So introduce this parameter called compressibility factor, Z, and define it. It's defined by the ratio of P times V over RT. Okay, let's define that compressibility factor that way. So what can you immediately say about this compressibility factor for a certain situation? Tell me something about this compressibility factor that you see from its definition. Say that again?
It's high for high pressure.
Okay. Yeah, pressure goes up, compressibility factor goes up. Sure. I buy that. Volume goes up, same thing. Inverse for R and T. Something else?
It's intensive.
No.
It's like,
Well, it is, but
it's like N.
it's like N. Which N? No. Let's go back to the ideal gas law that he was asking about in the red box, in the second red box. PV equals RT. Compare that to this. There was no N there. Anybody on this side? Compare those two, the one in the red box and the one on the right, and conclude something.
Z would be equal to 1 in the case of the ideal gas.
That's it. Right? You can immediately see that if you have an ideal gas, Z is 1. So that's important. So what you can see is, of course, this Z is sort of a measure of the deviation from the ideal gas behavior. And as you would expect, if the pressure goes up, Z will go up. Or if the temperature goes down, because it's the opposite criteria for temperature than for pressure, then Z goes up too, right? So that's what the compressibility factor is. It's nothing but a modification of the ideal gas law, because now I can write PV equals ZRT. The reason why it's not N, like you were saying, is because this is not the R that you see there, the universal one. This is the gas R, which we have gotten rid of the N by introducing the gas constant for the one gas that we're dealing with. So what she said, of course, is this. For an ideal gas, Z is equal to 1. So you have then charts like this. Here's nitrogen, which we were talking about. These tables are available to us because obviously now we need to have a place to find our Z. Right? If we're not going to use the ideal gas law, we need to get the Z somewhere. So there are charts like this. And as you can see, this chart is for nitrogen. But what this chart does for you is, if you know your pressure and your temperature, you go into this chart and read the value of Z. So pressure is on the horizontal axis. You can see it there in megapascals. The vertical axis has Z, the compressibility. And then the lines that you see here, the different lines are for different temperatures. So let's say that your, pick any random value. Say that your pressure is 10 megapascals and your temperature is 200 Kelvin, then you would look for the intersection of 10 megapascals with the 200 Kelvin line, and then go to the left and read a value, say me about 0.8, roughly, eyeballing it. So that would give you the number that you have to put in here. Now, I added here 0.1, which is, of course, which pressure? Atmospheric pressure, right? 0.1. You can see how all of these temperature lines converge. In fact, they crammed up so much that they don't draw them all the way, but they all crammed up to 1. This middle line is 1, so that's ideal gas. If you happen to hit a value of 1, that's ideal gas. So 0.1 atmospheric pressure is sufficiently low for nitrogen that pretty much independent on which temperature you take, you're going to be with a Z value of close to 1. And also, if you go to very high temperatures, so the temperatures go up that way, you also start converging onto the line of 1. So you can see how the ideal gas law is verified. But what this does is will give you Z. But then you will need a table like this for every substance. You need one for nitrogen, another one for oxygen, and so on. What is nice is that you can develop what is called a generalized compressibility chart. If you define two quantities, the reduced temperature and the reduced pressure. So take these as two definitions, reduced temperature and reduced pressure. We call them T sub r and P sub r. And what they are is just the actual pressure divided by the critical pressure, and then the actual temperature divided by the critical temperature. So assuming that I have all of that for my substance, then I can find these quantities, reduced temperature and reduced pressure. And then there are charts that are universal. So now you can go to a chart like this. It's a little fancier, a little busier, but you have it. It has the same features as the one that we saw for nitrogen. So, by the way, going back to this one, you can see the dome there. This is the dome. It just happens to have that particular look if this is what you're plotting. So saturated vapor, saturated liquid. And this is to warn you, of course, be very careful if you're trying to use ideal gas law for a liquid. And you will. Some of you will use in an exam, ideal gas law, even though you're dealing with a liquid. So if you're dealing with a liquid, of course, you are somewhere down here. You'll be somewhere on this side. Look at the Z. It's some number, 0.1, maybe close to 0. So that means that if you're using ideal gas law, you're going to get really wrong results. And so if we go back to this one, this is the so-called generalized compressibility chart. Now, I enter not with the pressure, but with the reduced pressure. I've already calculated the ratio of pressure to critical pressure, and I enter with that here. And then the temperatures, instead of being the actual temperatures, are T sub R, the reduced temperatures. So, but it's read the same way. If you could enter with a reduced pressure, intersect the curve for the reduced temperature, and then read your compressibility, your Z. And that's the one that you will use. So then instead of using the ideal gas law, you use this. You use PV equals ZRT. All right? And that's your equation. All right? Any questions about this compressibility chart? I have time to work on an example just to show you the difference. So it's, again, a very simple problem, even simpler than the other ones. It's 294. A tank has argon. We know the volume of the tank. We know the temperature of the tank, or the argon in the tank, and the pressure. And we're asked to find the mass. That's it. Very simple. So what do I do? Obviously, it's an application of what we just learned. So what I'm going to do, first of all, is go to that table of critical constants and look for argon. So it's the second entry, second line, argon. I read there my critical temperature, 150.8 Kelvin, and critical pressure, 4.87 megapascals. Write them down here, and then from my definitions of reduced pressure and reduced temperature, I can immediately calculate those. Reduced pressure, reduced temperature. Always be very careful when you're doing these problems. When you're doing ideal gas law, the temperature must be in an absolute scale. Right? If you decide to go ranking, that's fine. But it has to be an absolute scale. If you plug in a temperature in Celsius or in Fahrenheit in the ideal gas law, you get all wrong results. So the one thing that you have to do here before you do the calculation of the reduced temperature is convert it to Kelvin. So the minus 30 plus 273. So in the end, you have a reduced pressure of 0.62 and a reduced temperature of 161. That allows you now to go to the compressibility chart. 0.62 and 161. So 0.2 somewhere 2, 4, 6, somewhere around here. And what was the other one? 161. Wherever it intersects the 161, I'll get a number. So I'll go there and find a number. In this case, it's not bad. It's 0.96, the Z, because I picked values that, as you could see, gave me numbers that are close to 1. So I already know that I wouldn't expect a huge error if I use the ideal gas law. But this is the way, if I want to be very precise, then I have to put this Z into my equation that includes the compressibility factor. So PV equals ZMRT. Note that I rewrote it now in terms of the volume, not the intensive volume, so the mass shows. So that's what I want. I want to solve for the mass. And I get that, so I plug in all the numbers, I get 309 kilograms. I already know what kind of error I'm getting if I had decided not to use the compressibility chart and go ahead and do it with the ideal gas law, what kind of error am I going to have?
4%.
About 4%. That's obvious because we are 4% away from 1 in Z. So in this case, the error is not big. If you do ideal gas and redo the calculation, instead of getting 309 kilograms, you'll get 296. You know, in many situations, that might not be bad. That error, 4%, might not be a big deal. In some other situations, it might be. Or if the problem happened to have had a different pressure or temperature that would have produced a value of Z much farther away from 1, then, of course, the error gets larger. Question there?
Do you have to check whether that Argon is a gas or not?
Well, it'll be a gas because of the particular conditions it's in, right? But yeah, if you're in doubt, you would have to check. Certainly, if the pressure is very, very large, you could make it liquid. But you see, this is not an extremely large. It's less than critical. So it's not under conditions. But yeah, I mean, that could be a situation that you have to check that it is a gas. Yes?
Would you have to use like a different compressibility factor if you're changing your state from two very different pressures or temperatures?
No, this chart, if I understand your question, this chart is universal.
No, I understand that. I'm saying, like, let's say you start at a state that has a compressibility factor or something, then you go to a different state that's very far away.
Oh, yeah, I see what you're saying. Yeah. And at the new state, so for example, let's say that this was the initial state, and you found that Z and you found that mass. But suppose that what you're saying, at the end state, the conditions are different, and the Z is different. Then if you want to find data for that final state, then you need to find the new Z. Right? So the Z could vary during the process, just like any other property can vary during a process. That's a good question. Any other questions? Okay, I think I will stop here. We're about 10 minutes left, but when we come back on Tuesday, we'll start talking about the next chapter.